we kind of jumped forward yesterday so we could talk about the eye. So I'm going back to talking about mirrors again for a little bit. You're a good man, Trace, I just have to say. So let's just get right into it. First, 2 review slides from yesterday. One is a slide, one is actually something to calculate. So you got a piece of paper just to make sure we can all go through the problem. For refraction, we had Snell's law. Which says N1 sine theta 1 equals N2 sine theta 2. Really important to remember this one here. You must measure the angle between the surface normal and the incident ray. And just like with reflection, the refracted ray is going to be in the same plane as the surface normal, the incident ray. And the last one is a does statement. The incident and transmitted rays are on opposite sides of the normal, right? It doesn't refract back like this. Okay, so given that, we have a beam that strikes one face of a window pane with an angle of incidence of 30 degrees. The angle of refraction of glass is 1.52. What's the angle, or what's the angle, the index? What's the index of refraction for air? 1, right. So I didn't write that. The beam travels through the glass and emerges from a parallel face on the opposite side. Ignore reflections. There will be some reflection. Ignore it. Find the angle of refraction inside the glass and show that the ray that exits is parallel to the incident ray. So 2 pieces to the problem. I want people to work through this just to make sure they understand it.
It's so sad. Yeah.
Chocolate everywhere.
Yeah.
All right, so good glass. We have light angle, a 30-degree incident.
Just can't use this today. Is this for refraction?
Yes.
30 degrees. So we know the law. Snell's law is in theta is but obviously the convenience.
What's the thing? Oh, it goes into glass. Glass is
We have 1 sine of 30 minus 1.52. The inverse of that. So the sine inverse of I got it.
Are we doing this as in group or individual?
You can work as a group or individual, whichever you're comfortable with.
So A is done. You show that the rays on either side of the glass are parallel to each other.
Yeah. Like,
Should you just draw a picture of the big parallel?
It's moving through the
I'll
air.
show it.
It goes from air to glass to air.
Oh.
The idea of you to say this thing.
Okay.
Well, we know that it's going to be distorted within it, and then it's going to hit the other side of the glass. And we know that when
So it
these
goes.
things are reversible, right? So then it'll just go back to the way it was. And the way it was will be parallel. Oh, yeah. So like it'll look like this.
Hang on.
And then you still have your
Oh, do you mean like?
So it'll work
Oh,
right.
yeah, I like 19.
So the emerging
On top, and then it'll refract the unit.
today's
You can't go back on like that.
And you have to do the same thing that
More, and then go back. Oh, you're right. It'll be parallel.
Helping them.
Only one I'm grading.
One in the middle of that.
tomorrow I'm gonna be glad to be
Roasting
like
you.
every day.
You can turn on.
My painting was like.
I'm not.
Okay, so the angle of refraction,
It's nice.
Yeah.
does it goes from here, right? Where does it go from here?
Yeah, that,
That's my
yeah, that's good.
It can't be the same size.
Okay. Oh, so.
Trace, why don't you take my light blue marker? Just don't touch the dark purple.
I know, I'm looking at it.
So you got this, right? That's the first ray. And then it goes through.
We're gonna say that those two are parallel. Yeah, this one goes steeper. I didn't, that's.
I'll just.
So you just want us to draw it?
Well, I want people to calculate what the angle is.
No, for part B.
Oh, part B, yeah, calculate the angle again.
So, calculate it again.
So that
Is this
turns into
a good depiction of what's going
I
on?
meant you to do.
Okay.
I'm like, calculate.
I don't hope so, I drew it.
Yeah.
It makes sense to me. Just like draw.
We're all in this together. It's like high school.
Crazy. Stop.
Sure.
It's gotta be a big one.
I mean, the calculation is simple. You just put, and then flip back.
You just try to.
What? Say that again? What M lived that? That's all I heard. I was like,
Let us call these.
Theta 2, this would be the N2, which is 1.52 times the theta that we got here. So sine 19
Yeah.
divided by 1.
Okay, I've given you some time to work on it. Obviously, we can't spend the entire class period, so I'm going to now go through the solution. So the first step is, of course, to draw a picture. So there is my glass. And then not a force diagram. Then I have my incident ray. Oops. My incident ray is coming like this. And I measure the angle from what surface? The normal, from what line? The normal to the surface. So I draw the normal here. Okay, I almost made it. There's my surface normal. So my angle of incidence is theta 1 equals 30 degrees here. And I have N1 is equal to 1.00. Now it goes into water, and the water has N2, or not water, glass, of 1.52. So the first thing I'm going to do without any calculation is the statement that we learned yesterday. If it goes into a slower medium, which way does it bend? Toward. It bends toward the normal if you go into a slower medium. So that means my light must be bending like this. Okay. Me in straight lines. Bending like this. And so my angle of refraction is there. Now it's going to hit the second surface. And so at the second surface, I'm going to have a new normal for where it hits the second surface. And now it goes from slower to faster. How do I know it's going from slower to faster?
Because the difference is in the, I'm trying to word it.
Index of refraction, the indices of refraction. So it's going into a faster medium. So what direction is it going to bend now? Away from the normal. So it's going to come back out like this. And now my picture doesn't show them as parallel. That's okay because, before you start, you don't necessarily know that. So there I have a picture to depict what's going on. And then I apply the single rule that I have to tell me what's going on at each boundary. So at the first boundary, n1 sine theta 1 equals n2 sine theta 2. At the second boundary, n2 sine theta 2 equals n3 sine theta 3. Now I'm one step away from having part B done. Where's the angle of incidence for the second boundary? So the second boundary is the lower one. Where's the angle of incidence going to be?
Between that and the second one.
Yes.
Yeah.
Now I've labeled it theta 2. In this case, it is theta 2 because my top surface and bottom surface, I'm told, are parallel to each other, which means that the surface normals, the black lines, the black dashed lines, are parallel to each other. And so my light ray that's going through the glass is crossing two parallel lines, so the angle between them has to be the same. So using a geometry rule, I know that my theta 2's are the same. And so the reason I am now done with part B is because n1 sine theta 1 equals n2 sine theta 2, but n2 sine theta 2 is equal to n3 sine theta 3. So since n1 equals n3, then sine theta 3 has to equal sine theta 1, which means theta 3 has to equal theta 1. So I didn't even need to do a calculation there because the equations showed it out. Okay, Leslie had a question.
So why do we have to focus on that second angle and not just, like, who cares about that one and just do the one that's closest to the normal?
Well, because I want you to have practice doing it, and because there's going to be something else I want to mention. And so let's do the second angle, and then I'll talk about the other thing I want to mention. So calculating what theta 2 is, I'll just take this equation here. I'll get rid of my box and underline that I used to identify which piece is which. If I want to solve it for theta 2, then I have to divide both sides by n2. So I have sine theta 2 is equal to n1 over n2 sine theta 1. And then how do I change from sine theta 2 to getting theta 2? Inverse sine. So I'm going to do, and I'm going to put a sine today for inverse sine. So I have 1.00 times sine of 30 divided by 1.52. And then I do arc sine of that. And I saw a lot of people did that. And what did you get for your answer?
19.204.
So theta 2 is 19.2 degrees. Now, as Leslie asked, why did we want to calculate this? Well, I want to make sure people can do the calculation correctly. And I wanted to show that if there had been no glass, then it would have just gone like that. And so I have a separation between where the light would have been and where it is now. So it's going the same direction, but it's separated. So when you look through a window, you don't see any kind of separation because you're looking through one plate, one pane. But if you had a window and the piece of glass just ended, you would have a jump between what you're seeing because of this horizontal shift disappearing when you go into having no window. And so I don't know, I may read books about who are taking a shot, from 1,500 meters through a glass window. Well, when it's going through that glass window, you have to take into account you're going to have a shift in the bullet because what you think you're shooting at is not where it actually is because of that effect if you're not looking directly in normal. Somebody over here has a question.
So if you had like a pan glass, nothing but a pan glass,
Yeah.
would theta 1, theta 3, and theta 5 all be the same?
If everything's parallel, yeah.
Okay.
We deal with cases where they're not parallel.
Sure. Yes. What fun would life be if we didn't? Now, find an image in a plane mirror. We had a previous question about how much mirror a person needs to see themselves. But now let's extend that question to where do you see yourself? When you stand in front of a mirror, where is the image? The image is what you see. So your brain is taking the rays that come to your eye and saying, okay, it goes back and out there is where the thing is I'm looking at. The thing your brain thinks it's looking at is what we call the image. The object is the actual thing that was the source of what you're seeing. So where does your brain interpret your position when you look at yourself in a mirror?
Equidistant on the other side.
Okay, the correct answer is equidistant on the other side. So if the mirror's right here, my brain's going to say that I'm back here. How do we get that equidistant part?
By extrapolating from
Okay,
AC or no.
by extrapolating. So in this picture, you can see the extrapolations done for you. You have a certain size of your iris. And that color is a horrible color to use. You can't see any contrast. You have a certain size of your iris, which means that rays coming from a single point on the object will be coming through the entire iris and then going back to the pupil. Iris. Pupil is the hole in the iris, just in case you get confused by the words. To the retina, where they're focused. And then your brain takes that and says, well, those rays that came to a focus on my retina must have originated, and it just extrapolates back and says, the two came together there. Because angle of incidence equals angle of reflection, this here is an exact mirror image of that ray. They're exactly the same. And so the distance for those rays to extrapolate and come together is going to have to be the same distance as they were away here. Now notice this is a front surface mirror. That is, the reflective surfaces on the front. This is what you would have if you looked into a very flat piece of aluminum, let's say, right, which used to be used as mirrors. These days, we can make really flat glass. Do you know how they make flat glass? I think it's something like they float the glass on molten aluminum or molten tin or something crazy like that. That's how they get it so flat. It's actually kind of awesome that people have figured out these things. So we make very flat glass, and then we coat the glass with the metal. But of course, when you coat that glass with the metal, one of the things you don't want is for that metal to come detached from the glass. And so usually you have glass on the side you see, and then the film is on the back side. And then they'll put something over it usually to protect it so it doesn't get scratched off. So usually you don't have a front surface mirror like this, you have a back surface mirror. Now I am going to, right here, go into something that I mentioned yesterday that's not at all part of my lecture. A one-way mirror. How does a one-way mirror work?
See through it one way, but only see.
Okay, the basis of a one-way mirror is here's my mirror, and I have a person here, and a person here, and this person, when they look at the mirror, they see themselves. But the person on the other side, when they look in the mirror, they see light coming from the person on the other side of the mirror. How do we make this happen? And it's not magic, but it is kind of a trick. It's not just what you see there. That's just the way it seems. So the way this works is you start with this mirror is a 50% reflective mirror. So it's 50%, then that means that the light given off from each person, because each person is giving off light, half of it is reflected back, half of it goes through. So how can it work that you only see light? You see light from the blue man coming through, but you don't see light from the red person going through. I'm trying to change colors. How can that work? Like I said, it's not magic, but it's kind of tricky.
One side at like an angle or something?
They're both the same as far as that goes. There's a difference in the two sides. What was that?
The surfaces are different on each side.
Okay, one thing I should specify, because I think this is what you were saying. If it's 50% reflective, it's 50% reflective on both sides. It's not more reflective on one side than the other, which most people think it is. Most people think it must be reflective on one side and not on the other.
Oh, right.
Is it the amount of light difference?
Yes, it's the amount of light. This person here is in a bright environment. And so the amount of light coming off of them reflecting from the environment is large. This person here is in a dim environment.
So if you,
Do not misread this. We're talking about intelligence. This is talking about light.
if you cover your face and look through the right side, can you see it? Everything on the other?
That's, yes.
Oh, well, the police can't do that to me then.
That's
They'll probably also cuff you to a chair.
That's what I used to do in the music room. I wonder who's in there making that beautiful music. Mira.
I like some TV shows like a lighter for the mirror to see if it's two-way or one like.
I haven't seen that on a TV show, but
TV shows are sketchy.
they are kind of sketchy, yes. But that's how this works. So something you do see on TV shows or in like comic strips, this person is behind a one-way mirror, so you can't see who it is for, it's him. And then a janitor turns on the lights in the dim room, and all of a sudden the other person can see who's identifying them, right? Because that's what would happen. Because the bright side has a lot of light, so a lot of light gets reflected back, so they see themselves. The person on the dim side, it's dim, so they get a dim reflection, but they have a lot of light coming from the other side. And so they see the light from the other side primarily. Yeah.
So that was going to be my next question. If they were to make that side brighter, then but then I'm wondering how they make that mirror. Like, I'm not fully understand how you would make a one-way mirror and then a two-way mirror.
Well, the one-way mirror is the only thing that makes it a one-way mirror is 50% reflective.
Okay. Are most less than that?
Most mirrors are 100% reflective,
okay.
Or 99 point something, pretty close. And so how they make it, and I say 50%, it may vary, because depending on what the percentages are, you'd have different ratios of light on each side that you need to make it effective. But you make it like 50% reflective by having the coating not complete. So where you have coating, it reflects. Where you don't, it doesn't. And it's just, not a complete coating. So it looks kind of grayish because it's not complete. So that's how one-way mirrors work. Why did I mention that at this point? Because you'll see really stupid things like, how do you know when you're in the bathroom that there's not a camera behind that window or that mirror, that's not a one-way mirror? Has anybody read those things, or is that like 5 years ago? And what was the bad advice that they gave you? Yeah, touch it. And I don't even remember what they said. All that touch test tells you is if you have the mirror coating facing you or not. But the one-way mirror could have the mirror coating sandwiched between two pieces of glass, or it could have the mirror coating facing you or away from you. It's not a definitive test in any way. And you would always expect every mirror, probably, you're going to touch it and you're going to see a reflection of your finger with a little gap because the light's going through the glass to the reflective surface and back, because they don't want you to have direct access to the surface that you could damage. So that was a very poor way of testing. All right. I talked about this. I think I showed this. I may or may not have showed the slide yesterday, but this is now going to be something important. When we talk about object distance and image distance, in this picture, here's the object. The object distance, we're always going to have a positive object distance except for some very special cases. The object distance is, by convention, positive and on the left side of our optic. So this is a positive object distance. For a mirror, the light should reflect. So if the image is on the side where the light goes to when it hits it, then the image would be positive. So if the image was on this side, it would have been a positive image distance. But here it's on the other side. The light's not supposed to go there, right? And so the side where the light's not supposed to go is negative. So the image distance for this plane mirror is negative. So the correct way of writing this is distance image equals minus distance object. We often will say it's equal. What DJ said was absolutely correct. The same distance behind as it is in front. That takes away all question marks. But the image distance, if we're going to write it down, is minus the distance object. It's a negative distance. DJ.
So for questions and stuff, it would be the same distance, but since it's factoring in the surface of the mirror, we have to subtract out.
Yeah, it'd be distance from the front surface. And we're not going to try a trick and say, and the mirror is 0.25, centimeters thick.
Yeah, because it seems like it's two things added up to equal.
Yeah.
Okay.
It'll be a mirror of negligible thickness.
Okay, so we don't have to worry about
Yeah, you won't have to worry about that. Okay, so that's how we get the object and image distances. Now, this has some different words. This says a real object has a positive and a virtual object has a negative. The virtual object is the odd case that we'll see later. So don't worry about that right now. For this point in time, just say the object distance is always positive. And then later we'll see a case where we can introduce a negative. The image distance, it says it's positive if it's a real image. Well, what would a real image be versus a virtual image? We kind of talked about it yesterday, but didn't carefully define it. So this here is a virtual image because the light rays didn't actually get there, right? It's on the wrong side of the mirror, as I said. So it's a virtual image, and that makes it so it has a negative image distance by the convention shown on the next table. So a virtual image will have a negative image distance. A real image, which is an image where the rays actually meet, you could put your hand there and you could see the image on your hand. So like right here, you can see the image on the screen. That means it's a real image. If you can project it, it's real. Then that's going to have a positive image distance. Right now, these seem unimportant, but they will be important soon. And then we have the focal lengths and the magnifications. If you have something upright, this is upright, it has a positive magnification. If it's inverted upside down, then it has a negative magnification. So, and the last thing here is focal lengths. Let's play around before I go any further. This here is not a plane mirror. What would you use to describe the surface of this mirror?
That's convex.
It's convex. It sticks out. And so I will have Wesley look at yourself in the mirror. Can you see yourself?
Yeah.
What do you look like? Is it upright or inverted?
Upright.
Okay, he's upright. Right away, because he's upright, is that going to be a virtual or a real image?
That's real. That's
But it's
virtual.
virtual.
what he's looking at is
Okay. Upright image was positive,
Yeah.
and so we have a oh no, that's positive magnification. Excuse me. Yeah, we don't have the words there to specify it, so I can't point to that and say you should have known. Okay, this is because it's upright. It's going to be virtual
Interesting.
with a single mirror or lens. If it's upright, it's always going to be virtual. And if it's inverted, it's going to be real. Now, second question that I don't think I asked, are your eyes look bigger than normal? looks smaller.
It's like at the distance that it looks like it's
Normal. Okay? So I'm going to bring it in. How are things changing?
magnified.
Okay, it's getting bigger. Is it bigger than your face or the same or smaller?
I'd say the same.
Well, it was the same back here. You said it's magnified. It can't be the same both places.
Okay, it's bigger.
Okay. As you bring it closer, is it bigger, smaller?
Bigger.
Okay. So there was not a lot of things changing with this one. It was, did it stay upright or did it go inverted?
Upright.
Stayed upright the whole time. So that's kind of boring. This one here, can you see yourself?
Yeah.
Are you upright or inverted? Okay, he's inverted. Inverted, is it a real or virtual image? Real. Inverted is real. Which side of the mirror is the image if it's real? It's on the same side as the object if it's real for a mirror. And are you larger or smaller? Okay, smaller and inverted. Now I bring it in. What's happening?
Larger but still inverted.
Larger but still smaller than real life. Is that what you said? And still inverted. Keep going. What we got now?
Wow. Inverted. And I guess increasingly larger.
Okay, is it bigger than your face or smaller?
I can't see.
I'm not sure how to angle it.
Up a little bit.
Up a little.
Only
Until the back.
and then off the point towards the middle.
Okay. It's bigger.
Okay, bigger. Now I bring it even closer. What do you see now?
Erect.
Okay, he had to put his head in because at the distance I put it, I describe it as a meat pie. You really can't see your face anymore. You see flesh tone, and you have no defining things. But we bring it closer, it became upright. What happened then when it became upright?
It became virtual.
It became virtual. So the image was moving to this side. So we're able to make an image on both sides depending on how far away the object is. Now, when it was that I can't focus on anything, I just see flesh tone, what was happening is it was creating an image that was closer to his face than his near point. In fact, probably he's making an image behind his head. You can't focus on things behind you, right? And so there was nothing in focus. So it's a lot more interesting looking at this. How would you describe this shape?
Concave.
Concave. Now, let's turn to this demonstration. And sorry, I gotta turn off these lights. So, back to the stuff we were working with last class period. Now I have a couple mirrors here. And we'll start with the convex mirror. If I put the convex mirror up there, what do you predict is going to happen? It's going to do which one?
I'm sorry, what did you say? Convex?
The convex one, this one.
It's going to diverge.
Okay, it's going to diverge is the prediction of one DJ Henderson. Who has his finger up.
Wait. Convex.
No, this is concave. Or
Concave?
convex, I mean, no, there's concave. Right. Convex, well, I keep going back for it. This is convex.
Okay, convex will come in. Concave will go out.
Okay, so
Convex is going to come in. I don't know.
this being physics class, of course we have to test it out. Okay, so you were right the first time. It's going to spread out. A convex lens converges, but a convex mirror diverges. The reason is actually real simple. Remember, light is going to have angle of index, or angle of incidence is equal to angle of reflection. And those angles are measured from the surface normal. So down below center, the surface normal is pointing down. So it's going to bend down. Up above, it's above it. It's going to bend up. So does this focus the light? Do parallel rays come to a focus? They don't come to a real focus.
They come to a virtual.
But you have a virtual focus. So this would have a virtual focus that we would get by extrapolating back here. Whoops, that missed. Still missed. So we have a focal point there. That's a negative focal length because, once again, it's on the wrong side. It's on the side the light doesn't go to. So this is a negative focal length. For this kind of mirror. And this is the convex mirror. So now I'm going to change to the concave mirror. And what's going to happen with the concave mirror?
Now it's going to come back.
Because the surface normal was now, if you're in the top, the surface normal is pointing downward, so it bends downward. And so here, it comes to a focus, and we can see right there the focal point, and that's a positive focal length. So that's the geometry of how a mirror makes an image. It's very similar to what we saw yesterday with how a lens made an image, right? And we have, again, a point that's the focal point that parallel incident rays go through. So the same things that we saw in class yesterday, or in lab yesterday, we're going to be able to apply for mirrors as well. In fact, we usually start with the mirror because it's the simpler one to look at. So I couldn't get this thing to work on my computer or on this, the optics workbench. The website still works. It's just apparently it's written in too old of a version of JavaScript for any of the browsers I was using. So if you can get this thing to work, it's really cool because it allows you to put in different light sources and see what's going to happen. And you can also have a lens versus a mirror. So since that didn't work, I have a much lamer one from, physics classroom. Pop-up block, perfect. Okay, escape, that's how we get out when I can't remember next time. So this has a lens, there's a mirror. I can change where my object is. And so you see with this mirror, if the object is farther than 2 focal lengths away, the image, can you see where I'm pointing here? Does that show up? Okay, so the image is right here where the rays meet. It's inverted. Does that make it real or virtual if it's inverted? Real. The rays actually meet. That also makes it real. Right? So real and inverted come together. Now, if I bring my object in, what's happening to the size of the image? It's increasing, but it's still smaller than my object. If I bring it in, so my object is at 2F. Okay. There. Now the object and image are at the same location, and they're the same height. So the magnification is 1 here. Actually, magnification is -1 because it's inverted. The my sign means inverted. So it has a magnification of -1. If the object distance is bigger than 2 focal lengths, then it has a magnification that's still negative, but less than 1 because it's diminished in size. If I bring it closer than 2F, now it's magnified. The magnification is still negative because it's still inverted, but it's larger. So it's going to be magnification of, in this case, about 1.8. Now, this is the one that was interesting, right? If I bring this closer than, now, this is a situation where he saw the meat pie. Because if Wes's head is here where the candle is, it's forming a real image that's back behind his head. The rays are coming together and his eyes just can't focus on that. And so he sees light, hence you see skin tone, but you can't see any features because it's just the light's not coming together. If I get into the focal point, notice as I approach the focal point, my image is going to be way off the screen, very, very far away. But if I get past the focal point, now the image shifted to the other side of the mirror. So when I brought it really close to Wes's face, he saw himself again, but now it's magnified and upright. Is it real or virtual? Virtual. Virtual because, well, upright meant virtual. Also virtual because, well, the rays aren't actually meeting over there. And then as I bring it closer still, we see it coming in. Now look at the rays that are used to construct this. Those rays are the same ones that we saw yesterday when working with the lenses. We have, what's the top ray called here? The parallel ray, or P ray, because it's parallel to the principal axis. And by definition, the parallel ray goes through the focal point. So here it was reflecting through the focal point. This one here, do you remember what that was called? Vertex ray. The vertex is the name for this point where the principal axis goes through our optical device. And the vertex ray, the surface normal is the principal axis, so angle of incidence equals angle of reflection. It comes back at the same angle as it came in. And then finally, this one here goes through the focal point, hence it's called the focal ray. And because it's the reverse of the parallel ray, it's going to come out parallel. And where those three meet, there's your image. You are on the test, not the test when we come back from break, but the one following that, you're going to have to do a ray diagram construction to show how an image is formed. That's going to be a question on your exam. So you have to know how to do this, what the rays are, and how to draw them.
So by that you mean it would be like a synthesis type thing, or would it be in the application part?
It would be a synthesis. Okay, apparently I can't make a negative focal length here. I can change the height. That wasn't my goal, but I can't change the focal length to make it a negative focal length because, well, that's half of the fun is changing it to the negative focal lengths. So that's one of the drawbacks of this app. Going back to my regular lecture. So in drawing these ray diagrams, I'm going to give you the practical tips. Always start by drawing your principal axis. Principal is in the primary or first, not principal is in, this is one of the principles I live my life by. Draw the principal axis, and then 2, draw your mirror, or if it's a lens. And how I draw the mirror or lens is interesting. Draw it as a straight vertical line. It could be concave, it could be convex. Draw this as a straight vertical line. Because with our approximations, we're approximating that the light is hitting the mirror at the same point in the horizontal direction. Not perfectly true, so it leads to some errors, but that's the way we're approximating. To indicate if it's concave or convex, I put things like that. That would mean that it's a concave mirror if I have my object on the left side. By convention, we put the object on the left side. Next, draw F and F prime. F is where the light comes to a focus. So for a concave mirror, where did light come to a focus? Same side or opposite side? For concave, it was on the same side. So for the concave, I have my F is here, and F prime would be over there. The F prime isn't very important right now, but it will be as we move forward. And then step 4, draw object. So here's my object. And by convention, we just use an arrow. That's the easy way of making your object. And it's the tip of the arrow that you're finding the image for. And then finally, step 5. So what's
The top one?
For constructing an image, we don't use the term incident now.
So the top one?
Yeah, actually, I don't care which one, but
Well, it matters. So parallel.
okay, parallel ray. So I'm going to draw the parallel ray first. And how does it reflect? By definition of parallel ray, it always reflects through the focal point. So there's my parallel ray. What's another ray? Somebody else. Don't want Trace to have all the fun. Someone else? Okay, vertex ray. So the vertex ray goes like this, and it comes back with the same angle. The way I get that same angle is I put a little measure straight below my object, that same height, and then I come back through that point. So there's my vertex ray. And what's my final ray going to be? The focal ray. And the focal ray, because light goes the same forward and backward, if it goes through the focal point, it must come out parallel. Now, this is a horrible construction. Not done with a ruler, right? Do it with a ruler. On the test, you'll want to use a straight edge for doing these. And if you do it carefully, you should find that they all come to the same location. Now, this was not close to the same location. If I was doing this and I got this on my test, I would go back and say, okay, which ray did I do a poor job on? Because they should come close. Now, you're never going to have them exactly on top of each other because ain't no one perfect, right? So if they're not exactly on top of each other, just take, okay, here's one location, here's the center one. I'm going to take that one and say, I'm going to use that for where my image is formed. But this would be very large errors, you can tell, because I'd say, well, according to my ray diagram, it's formed somewhere between there and there. Right? That's horrible bad. So I draw the three rays, and then where they meet, image is formed. So that's how you do it with drawing the rays. Now, this was one case where I had the object farther away than the focal point. If it was closer than the focal point, I would have had a different result. I am going to draw one more real quickly. Okay, start with a horizontal line. I can at least do that right. Horizontal line, and then I want to make a vertical line. Okay, where's my little ruler? Yeah, this isn't the one that had the ruler tool. So here's my vertical line. Perfect. Vertical line for my mirror. I'm going to make the mirror like this. What kind of mirror is that?
You're looking at it from the left side?
Yeah, we're looking at it from the left side. It's convex. Next, I'm going to put my focal points for the convex mirror. The primary focal point is on the opposite side, and the secondary is on the object side. Then I'm going to put my object and make my rays. So parallel ray, where's the parallel ray going to reflect to? The focal point. Well, the focal point is down here. So it's going to reflect as if it came from there. Because the light can't actually get there, it was a virtual focal point. My next ray, the vertex ray. Goes like that. And then my final ray, the focal ray. Focal ray. It goes through the focal point, right? Where's the focal point? Behind it. So I'm going toward the focal point, but then it's going to reflect out parallel. Whoops, wrong side. So I've drawn the actual rays here. Now I'm going to erase this dashed one because it will be a confusing one. because the rays don't actually meet, I don't have a real image. But I extrapolate the reflected rays. So I'm extrapolating back the reflected ray. You can see why I erased the other one. Extrapolate back this reflected ray. And where they all meet is where my image is.
So when the arrow is crossing, it's a real image?
If the light really crosses, then it's a real image. Now, this is the ray construction. You can do this algebraically, actually much more easily, using the same equation we learned yesterday. So for your homework problems, most of the homework problems are going to be using this equation. But you may have a ray construction homework problem where you have to understand what the rays are. Okay, I'm 2 minutes over. Sorry about that. We got to go.